In section 2.7, we're going to talk more about distance problems, and our prior examples had a single car or a single train traveling a certain distance. In section 2.7, there are going to be two different trains or two different cars or two different people walking, and we're going to be comparing how quickly they are traveling with each other to solve those type of problems. And then we'll also solve money problems. Those are collection problems, like if you have so many nickels and so many dimes that total up to a certain amount, or it might be how many $20 bills and $10 bills do you have. And then lastly, interest problems. That's interest that you receive on financial accounts, how much money you'll make with a bank statement. So let's talk about distance problems. We know that distance traveled is how quickly you're traveling and how long you're traveling. So distance equals rate times time. That's if there's a single car. But in section 2.7, we're going to be looking at two different travelers, two different trains, two different boats, two different people. And there are basically two scenarios. Scenario 1 is they have the same starting point. One travels and they have the same starting point, and another one travels, but one has a head start. One gets started an hour earlier or 2 hours earlier. So this train, or let's say, this car is traveling at a certain rate, 30 miles an hour, and he's been traveling for 5 hours. And this guy is maybe he's going faster, he's going 10 miles an hour faster, but he's only been traveling for 4 hours. When will they meet? When will the distance of car 1 equal the distance of car 2? When will the two distances equal each other? That's your first type of problem. They start at the same place, but one has a head start, and they are definitely traveling at different rates. The second scenario is they start, let's say trains, but it could be buses. They start at the same spot, but they travel in opposite directions. One person's traveling east, and the other person is traveling west. So as time goes on, these cars are getting closer to each other. Here, as time goes on, these cars or buses or trains are getting farther apart. And here, this is going to be their total distance apart. So this guy traveling west, he's traveling at a certain rate, and he's been traveling for a certain amount of time. And this guy going east, he's traveling at a certain rate, and he's also traveling for a certain amount of time. So for these, the total distance is going to equal the distance of car 1 plus the distance of car 2. Here it's when the distances are equal to each other. Here it's when, since they're going in totally opposite directions, we have a total distance. We're going to add that distance and that distance. This could also count if one is going north and one is going south, as long as they're going in exact opposite directions. All right, so let's go and practice our first one here. Here we have a jet traveling at 550 miles per hour. So jets travel very fast, 550 miles an hour. And that jet is going to overtake a small light plane, maybe a prop plane that's only traveling at 180 miles per hour. But the plane that's going slower, the prop plane, had a 1 hour head start. How far from the starting point? In other words, what's the distance are the planes when they meet? Okay, so here's the small plane, and then here's the jet plane. They're both starting at the same point. This distance is the jet plane's rate times their time. So the jet plane is traveling at 550 miles per hour, not 500, 550 miles per hour. And how long has he been traveling? Well, we don't know, so we'll call it time t. Here's the small plane. His distance is also equal to his rate times his time. But he's traveling at 180 miles per hour. And we don't know his exact time either, but we do know that it's the time the jet has been traveling plus 1. So if he's in the air for 4 hours, he's on the air for 5 hours. If he's in the air for 8 hours, he's in the air for 9 hours. When are these two equal? When does 180 times t plus 1 equal 550t? So when I solve this, I'm going to get the amount of time the jet plane was in the air. And if I add an hour, that's the time. Notice they didn't ask how long before they are equal to each other. They asked the distance. So once we get the time, we're going to have to go back and figure out the distance here. But let's go ahead and distribute the 180. 180t plus 180 is going to equal 550t. So we're going to move this t over, subtract 180t from both sides. 550 minus 180 is 370. And now divide both sides by 370. And one thing I don't like about this problem is it doesn't come out to an exact number, so I'm going to use to 3 decimal places, 0.486 of an hour. Okay, so a little bit less than a half hour. They'll meet up. So you can see how, so this plane will be in the air for, the jet plane will be in the air for about a half hour, and the small plane will be in the air for about an hour and a half. That's when the jet plane catches up to the small plane. But what's the distance? The distance, we'll use this one, is going to equal 550 times 0.486. So the distance is going to equal 267.3, and that's going to be in miles. Remember to put your units. They both will have traveled 267.3 miles. It would have taken him an hour and a half, an hour 0.486, and would have taken the jet just 0.486 hours, but that's the distance. And like I said, I don't like this problem only because it doesn't come out to exact numbers. You have to do some rounding. So when they're going in the same direction, just at different rates, and one has they have different times, you set the distances equal to each other. Here's my second type of example, and that's when here we have 2 trains leaving Elgin at the same time. One's going east and the other's going west, so they're going in the opposite directions. One's going east and one's going west. So one's going east and the other train that's going west is at a speed or a rate 6 miles per hour slower than the other train. In 1/2 hour, the total distance is 45 miles apart. Okay, so don't fall for this problem here. 1/2 hour, that means my time is going to be 0.5. All right? So, the distance of the eastbound train is rate times time. Do we know his rate? We don't know his rate. But do we know his time? Yes. He's been traveling for a half an hour. So we're going to call that 0.5 R. How about the westbound guy? Do we know his rate? All we know is that he's 6 miles an hour slower than that train. So his rate is going to be R minus 6 miles an hour slower. But he is also traveling for a half hour. So the distance for this train is going to be 0.5 R, and the distance for this train is going to be 0.5 R minus 6. The total distance is when you add them. And we are told the total distance is 45 miles an hour. So the total distance is going to be the eastbound train distance plus the westbound train distance. We know the total is 45 miles apart. The eastbound train's distance is 0.5 R, and the westbound train's distance is 0.5 R minus 6. So now we're going to solve for R. Find the speed of each train. If we know how quickly this one's going, we subtract 6 and we'll know how quickly the other train is going. 0.5 R plus distributing the 0.5 R. 0.5 times negative 6 is negative 3. A half and a half equals a whole. 1/2 plus 1/2 equals 1. Minus 3. And so to solve for R, we're going to add 3 to both sides. So R is 48 miles per hour. So we look back at our original problem. The eastbound train is R, 48 miles per hour. The westbound train is going to be 48 minus 6, or 42 miles per hour. So the westbound rate is going to be 42 miles per hour. One's traveling faster than the other, but they've traveled for the same amount of time, and at the end of a half hour, they're going to be 45 miles apart.